A neutron star can fit inside the distance between two edges of a city, yet hold more mass than the Sunday. Beneath its dark, almost perfectly smooth surface, matter is pressed beyond anything that can be recreated on Earth. Atomic nuclei lose their familiar shapes. Neutrons move in hidden currents. Light bends so strongly that part of the far side remains visible. And somewhere deeper, below every layer that can be named with confidence, the material may be approaching a boundary where present physics begins to run out of words. Before the journey moves inward, consider taking a moment to make the room quieter. Lower the lights, let the air settle, and find a position that does not need to be adjusted again. A fan, a soft blanket, or the low background sound of the night may be enough. If these slow journeys through space help bring a little calm, subscribing, liking, or sharing the video allows more of them to be made. It is also always interesting to know where the night has reached each listener and what time it is there. A city still awake, a house already silent, or a room lit only by the screen, all become small points beneath the same sky. The path ahead begins with something familiar. Long before matter is compressed into a neutron star, it lives inside an ordinary star, held between gravity pulling inward and pressure moving outward. That balance can last for billions of years. Then the fuel changes, the pressure weakens, and the star is forced to find another way to remain whole. From the hot plasma inside the sun to the quantum structure of white dwarfs, each stage reveals another limit, another temporary form of support, and another step toward the dense interior of a neutron star. The descent begins in light, in the quiet furnace at the center of a star. The visible surface of the sun looks almost solid from a distance, a pale disk with a clean edge against black space. Up close, that appearance falls away. The photosphere is not a surface that could be touched or stood upon. It is a layer of glowing gas, several hundred kilometers deep, where light finally escapes freely enough to begin its journey outward. Granules the size of countries rise and fade across it. Hot material climbs from below, releases some of its heat, then sinks again along darker boundaries. The pattern never holds still. It is slow only when measured against the scale of a star. The temperature here is close to 5,500 degrees Celsius, high enough to make ordinary matter behave in unfamiliar ways, though not high enough to strip every atom completely. Some electrons remain attached to their nuclei, others move freely. The photosphere is therefore a mixture, partly gas and partly plasma, the electrically charged state of matter that fills most stars. Plasma does not need to look violent. It can move in long, quiet currents, guided by pressure, gravity, and magnetic fields. In the sun, those currents carry energy upward from regions that cannot be seen directly. A little more than a century ago, Meghnad Saha found a way to connect temperature and pressure with the degree to which atoms lose their electrons. His ionization equation allows astronomers to read a stellar spectrum and estimate what state the material is in. The idea is simple in outline. An electron remains bound to an atomic nucleus only while the attraction between them is stronger than the energy trying to pull them apart. Raise the temperature, reduce the pressure, or change the chemical mixture, and the balance shifts. More electrons break free. The atom becomes an ion. The same calculation also explains why a star's color and spectrum do not provide a simple inventory of its contents. An element may be abundant, yet leave only faint lines if most of its atoms are in the wrong ionization state. Another may produce clear lines from a much smaller amount. Temperature changes what can be seen. Pressure changes it again. Saha's work turns those patterns from a set of dark marks into a map of physical conditions, allowing light from the surface to carry information about matter that no instrument can collect directly. This is one of the first thresholds encountered on the descent into a star. Matter has not been destroyed. It has changed its arrangement. The pieces remain, but they no longer stay together in the same way. Below the photosphere lies the convection zone. Heat travels here through movement rather than through light alone. Warm plasma rises, cooler plasma falls. Each parcel carries energy for a time, releases part of it, and turns back downward. The process resembles water circulating in a heated pot, though the comparison soon becomes too small. Solar convection reaches across distances larger than Earth and continues for months. Magnetic fields are stretched, twisted, and folded into the moving plasma. At the surface, that hidden motion appears as sunspots, bright loops, and occasional eruptions. Deeper still, convection gives way to a quieter form of transport. In the radiative zone, energy moves mostly as photons. A photon is born, travels a short distance, is absorbed, and is emitted again in another direction. The path is not a straight line. It is a slow wandering through matter so dense that a journey which would take seconds through empty space can last for tens of thousands of years. The energy reaching the solar surface today began moving outward long before any human city existed. Density increases with every step inward. The weight of the layers above presses down on the material below, and the material below pushes back. The sun contains nearly all the mass of the solar system, yet it does not fall inward in a single collapse, nor does it expand without limit. It remains between those outcomes, held in a condition called hydrostatic equilibrium. Gravity pulls toward the center. Pressure pushes outward. At each depth, the two are almost exactly matched. The word equilibrium can suggest stillness, but the interior of a star is not still. Particles collide. Radiation moves. Nuclei fuse. The star loses energy into space every second. Equilibrium here means that change happens without immediately breaking the larger structure. The inward and outward influences remain close enough that the sun keeps its shape for billions of years. Near the center, pressure rises to hundreds of billions of times the pressure at sea level on Earth. The density reaches about 150 grams per cubic centimeter, several times the density of common metals. Yet the core is made mostly of hydrogen, the lightest element. Gravity has forced that light material into a state that could not exist naturally anywhere on Earth. Temperature rises as well, reaching roughly 15 million degrees Celsius. At that temperature, atoms have no lasting structure. Electrons move independently through a sea of bare nuclei. The hydrogen nuclei are protons, each carrying a positive charge. Positive charges repel one another, so under ordinary conditions, two protons do not remain close enough to join. Inside the solar core, the pressure is high, the motion is fast, and quantum physics allows a small fraction of those protons to pass through the barrier that separates them. Fusion begins. Most of the sun's energy comes from a chain of reactions that turns hydrogen into helium. 4 protons eventually become one helium nucleus. The final helium nucleus has slightly less mass than the particles that formed it. That missing mass appears as energy. The amount lost in each reaction is tiny, but the number of reactions is vast. Every second, the sun converts hundreds of millions of tons of hydrogen into helium and releases energy that moves outward as radiation and heat. The heat keeps the core from contracting too quickly. Radiation also carries momentum and contributes pressure of its own. Together, these effects provide the outward support that balances gravity. A star like the sun is therefore not held up by solid material. It is held up by energy moving through matter. This balance can be described through an equation of state. The phrase sounds abstract, but it refers to a practical relationship, how pressure changes when density, temperature, and composition change. In a gas at low density, particles have room to move, and pressure depends strongly on temperature. In a stellar core, the same broad rule still matters, though radiation, ionization, and quantum behavior add further layers. A softer equation of state allows matter to compress more easily. A stiffer one resists compression more strongly. For the sun, the equation of state is known with unusual confidence. Its surface vibrates in millions of overlapping patterns, each one shaped by conditions below. By measuring those vibrations, helioseismology reveals how sound moves through the interior. The result is similar to learning the inside of a musical instrument from the tones it produces, except the instrument is a star, and the tones are too slow, and too low to hear directly. Another message comes from neutrinos. These nearly massless particles are created during fusion reactions in the core. They interact so weakly with matter that most pass through the sun almost without interruption. Light may spend thousands of years finding its way outward. A neutrino can leave the core and cross the solar surface in only a few seconds. That makes neutrinos unusually clean messengers. Their numbers and energies depend on the reactions taking place at the center. They reveal that fusion is happening now, not merely that it happened in the distant past. They also help constrain the core temperature, because even a small change in temperature can cause a much larger change in the rate of certain reactions. The first efforts to detect solar neutrinos found fewer than predicted. For years, the difference appeared to suggest that something was wrong, either with the models of the sun or with the experiments. The answer came from the neutrinos themselves. They can change from one type into another while traveling, and early detectors were sensitive mainly to one type. Once that transformation was included, the missing particles were accounted for. The sun had been behaving much as the models described. The particles had been changing identity on the way to Earth. This matters beyond the Sunday. The nearest other stars are so distant that their interiors cannot be studied with the same detail. The sun becomes the reference against which stellar models are tested. Its vibrations, neutrinos, spectrum, mass, and brightness allow astronomers to check whether the same physical rules explain other stars at different stages of life. For most of its existence, the sun changes slowly. Hydrogen is consumed in the center, and helium accumulates. The composition of the core shifts. Because helium particles add less pressure per unit mass than the hydrogen they replace, the core contracts slightly. Contraction raises the temperature. Fusion then proceeds more quickly, and the sun gradually becomes brighter. The change is gentle on human timescales. Over billions of years, it is substantial. Hydrostatic equilibrium is therefore not a perfect balance that remains frozen. It is a continuing adjustment. Gravity compresses the core. Compression heats it. Higher temperature increases the fusion rate. Fusion raises the outward pressure and slows the contraction. If the core cools slightly, gravity gains ground, and compression restores some of the lost heat. The star responds to disturbance without needing any external control. This self-regulation gives ordinary stars their long lives. It also hides the fact that the balance depends on fuel. Pressure from fusion continues only while suitable nuclei remain available under the right conditions. Hydrogen in the central region is finite. As it becomes scarce, the reactions that once supported the core begin to change. The sun does not stop shining at once. Fusion moves into a shell surrounding the spent center, while the helium core contracts and grows hotter. The outer layers respond by expanding. The star becomes a red giant, larger, cooler at the surface, and far more luminous than before. The familiar equilibrium is replaced by another, temporary arrangement. Eventually, helium begins to fuse. Later still, that fuel also runs low. A star with the sun's mass cannot reach the temperatures needed to continue through every possible nuclear reaction. Carbon and oxygen remain in the center, but they do not ignite. The core has reached a condition in which heat alone is no longer enough to support it. Gravity continues to press inward. At this stage, another form of pressure becomes important, one that does not depend on burning fuel or maintaining a high temperature. It comes from the rules governing electrons. Those rules allow matter to resist compression even as the star cools and the last nuclear reactions fade. The sun's outer layers will drift away, leaving the core exposed as a small, hot remnant. That remnant is a white dwarf. Its support does not come from fusion. It comes from quantum mechanics and from the refusal of electrons to be placed into the same state. A white dwarf begins as the exposed core of a star that has finished using the fuel available to it. The outer layers drift away into space, leaving behind a sphere about the size of Earth, still hot enough to glow, yet no longer producing energy through sustained fusion. Its brightness comes from stored heat. Slowly, over periods longer than the present age of the universe, that heat leaks away. Sirius B is one of the nearest examples. It moves around the brighter star Sirius, hidden for much of history by the glare of its companion. Its mass is close to that of the Sun, but its diameter is similar to Earth's. The compression is severe. A small volume of its material would weigh far more than any ordinary substance found on the surface of a planet. There is no familiar solid lattice inside it, no arrangement resembling rock or metal. The atoms have been pressed beyond that. The nuclei remain, but the electrons move freely through the star. Gravity keeps trying to pull the material into a smaller space. Heat helps for a while, though a cooling object cannot rely on heat forever. A different kind of resistance appears, one that remains even when the temperature falls. Electrons belong to a class of particles called fermions. Fermions follow the Pauli exclusion principle, which states that two identical fermions cannot occupy the same quantum state at the same time. The rule does not come from particles colliding like hard spheres. It is built into the mathematical structure of quantum mechanics. Under ordinary conditions, its effects are easy to overlook. Inside a white dwarf, they become the reason the star survives. A useful picture is a building with many floors. Each floor represents a range of allowed energies, and each has a limited number of places. Particles fill the lowest available states first. As matter is compressed, the lowest floors fill. Additional electrons cannot join them there, even if gravity continues to press inward. They must occupy higher energy states. The crowding creates pressure. This pressure does not depend mainly on temperature. It comes from the forced motion associated with confining electrons to a smaller region. The more tightly the material is compressed, the more momentum the electrons must carry. Their motion generates an outward resistance known as electron degeneracy pressure. It can support a star even after nuclear reactions have ended, and the interior has cooled far below the temperatures of an active stellar core. The word degenerate has a precise meaning here. It describes matter in which the available low-energy quantum states are largely filled. It does not imply disorder or decay. Degenerate matter is highly constrained. Its particles have fewer available ways to rearrange themselves, and that restriction gives the material its unusual stiffness. A white dwarf can therefore remain stable without burning. Gravity presses inward. Electron degeneracy pressure presses outward. The balance is different from hydrostatic equilibrium inside the Sun, though the larger pattern remains familiar. An inward force meets a form of support created by the behavior of matter. The density changes how the star responds to added mass. In an ordinary planet, adding material usually makes the object larger. In a white dwarf, adding mass strengthens gravity and compresses the star further. The more massive white dwarf becomes smaller. That reversal is one of the clearest signs that the object is not supported by ordinary material strength. At lower masses, the electrons move at speeds well below the speed of light, and the pressure rises strongly as the star is compressed. The response is stiff enough to hold gravity back. As the mass increases, the electrons are forced into higher momentum states. Their speeds rise. Eventually, many move close to the speed of light. Quantum mechanics and special relativity then meet inside the same object. Once the electrons become relativistic, their pressure no longer increases quickly enough to match the growing pull of gravity. Compression still raises their momentum, but not in the same helpful proportion. The star approaches a mass beyond which electron degeneracy pressure cannot provide stable support. Subramanian Chandrasekhar works out this limit while still a young man. During a sea voyage from India to England in 1930, he studies how relativity changes the behavior of degenerate electrons. The calculation leads to a maximum mass near 1.4 times the mass of the Sunday. The exact value depends slightly on composition, but the boundary is real. Above it, a cold, non-rotating white dwarf cannot remain in equilibrium through electron degeneracy pressure alone. The result is initially resisted. A star supported by quantum rules is already strange. A star with a built-in maximum mass seems stranger still. Yet observations eventually support the calculation, and the Chandrasekhar limit becomes one of the central thresholds in stellar evolution. Below that limit, the exposed core of a sun-like star settles into a white dwarf. Its radius is determined by the balance between gravity and the pressure of its electrons. It may begin extremely hot, but it contains no long-term source of new energy. Its light fades gradually as heat escapes from the surface. The cooling is slow because the material is dense and the star's surface area is small. The ions in the interior store heat, while electrons conduct that heat outward efficiently. Over time, the core can begin to crystallize. The nuclei arrange themselves into an ordered structure, while the electrons continue to move through the material. A large fraction of some white dwarfs may already exist in this partly crystallized state. Crystallization releases a little energy and delays the cooling. The effect is subtle, but it matters when astronomers use white dwarfs as clocks. In a cluster of stars formed around the same time, the faintest white dwarfs reveal how long the oldest remnants have been cooling. Their temperatures and brightness help estimate the age of the stellar population around them. The outer layers of a white dwarf are thin compared with the whole star. Hydrogen or helium may form a shallow atmosphere above the dense carbon and oxygen interior. That atmosphere shapes the light leaving the surface. Spectral lines reveal which element dominates, though the main body of the star remains hidden beneath. Most white dwarfs are made mainly of carbon and oxygen, the products left behind after helium fusion in stars like the Sunday. Some lower mass remnants contain more helium. The most massive may hold oxygen, neon, and magnesium. Composition affects the exact relationship between mass and radius because each nucleus contributes a certain number of electrons to the degenerate sea. The star's history therefore remains written in its interior. The mass of the original star, the stages of fusion it reached, the amount of material lost, and any interaction with a companion all influence the remnant that remains. Gravity also separates the remaining elements with great efficiency. Heavier nuclei sink, while lighter ones float upward. Even a small amount of hydrogen can spread across the entire surface and hide the helium below it from view. A still thinner layer may determine the spectrum seen from Earth. The visible atmosphere can therefore give a misleading impression of the star's deeper composition. Some white dwarfs possess magnetic fields millions of times stronger than Earth's. The field can alter the motion of charged particles and split spectral lines into closely spaced components. Others rotate slowly, preserving angular momentum from the star that formed them. A few pulse as their brightness changes. These pulsations are not explosions. They are global vibrations, with different regions moving in and out in patterns governed by the interior. Asteroseismology uses those patterns in much the same way that helioseismology uses waves on the Sunday. Each oscillation travels through layers with different density and composition. Its timing carries information about the thickness of the atmosphere, the size of the crystallized core, and the transition between carbon-rich and oxygen-rich regions. The star remains unresolved as a point of light, yet its internal layering leaves a trace in the rhythm of that light. There is no single moment when a white dwarf becomes cold. Its fading continues through ages. Given enough time, it would become a black dwarf, a dark remnant with almost no heat left to radiate. The universe is not old enough for any black dwarf to exist. Even the earliest white dwarfs still retain some warmth. That unfinished cooling gives the night sky a population of stellar remains caught between their bright beginnings and a darkness that lies far beyond the present cosmic age. A lone white dwarf cools quietly. In a binary system, the story can change. If the companion star expands, gas may spill across the space between them and collect on the white dwarf. Hydrogen can accumulate on the surface until pressure and temperature ignite it in a sudden thermonuclear reaction. The result is a nova. The white dwarf survives, and the process may repeat after more material arrives. A different outcome becomes possible if the white dwarf gains mass steadily and approaches the Chandrasekhar limit. Carbon fusion may ignite throughout much of the interior under degenerate conditions. Because degeneracy pressure does not immediately respond to temperature, the heating does not produce ordinary expansion at first. Reactions accelerate through the star, and the white dwarf can be disrupted in a type Ia supernova. In another pathway, the core may collapse instead of exploding completely, especially if it is rich in oxygen, neon, and magnesium. Electrons are captured by nuclei. The number of free electrons falls. The pressure supporting the star weakens. Gravity gains ground. The same principle appears in the core of a massive star. Fusion builds heavier nuclei in layers, while the center moves toward iron. Iron cannot release energy through ordinary fusion under stellar conditions. Once an iron core grows too massive, electron degeneracy pressure becomes the last main support. The core is already close to the Chandrasekhar mass. Then electrons begin to disappear into protons. The reaction produces neutrons and neutrinos. With fewer electrons available, the pressure falls. The core contracts faster. Higher density encourages more captures, which removes still more electrons. The process feeds itself. In less than a second, a region thousands of kilometers across collapses to the scale of a city. The nuclei are crushed together. Their boundaries lose meaning. Matter reaches densities found inside atomic nuclei, and the collapse is halted by a new resistance. Neutrons, like electrons, are fermions. They obey the same exclusion principle, though the conditions are far denser and the forces between particles are no longer negligible. The white dwarf has reached the end of its role in the story. Its quantum support explains how a dead stellar core can remain stable, and its upper mass reveals when that support must fail. Beyond the limit, electron degeneracy cannot hold gravity back. Another form of matter takes over. The star becomes smaller by a factor of hundreds. Most of its mass remains. The electrons and protons that once filled the core have been transformed, leaving a compact remnant dominated by neutrons. A neutron-star is born. The birth of a neutron star begins before anything on the surface of the dying star reveals how quickly the center is changing. The outer layers may still glow with the colors of an ordinary supergiant, and the star may appear steady across many human lifetimes. Deep inside, however, the sequence of nuclear burning has shortened from millions of years to days, then hours. Carbon gives way to neon, neon to oxygen, oxygen to silicon. Each stage supports the core for less time than the one before it. At the end of that sequence, iron gathers in the center. Iron marks a boundary because fusing it does not release energy in the way lighter nuclei do. The core can still gain mass as shells above continue burning, but the reactions at the center no longer provide the pressure needed to oppose gravity. Electron degeneracy pressure holds the structure for a while, much as it does in a white dwarf. The difference is that the core is still being loaded from above. Its mass creeps upward. As the density rises, electrons are forced into nuclei. A proton captures an electron and becomes a neutron, while a neutrino is released. The number of free electrons falls, so the pressure they provide weakens. The core contracts. Contraction raises the density further, making more captures possible. The process accelerates until the core loses support in less than a second. Matter falls inward at a large fraction of the speed of light. Nuclei are pressed so closely together that the empty spaces between atoms disappear. The structure of ordinary matter is erased. In the center, density approaches that found inside an atomic nucleus, and the strong nuclear force begins to resist further compression. The inner core stiffens. Material still falling from above strikes this suddenly resistant region and decelerates. A shock wave forms and moves outward. At first, that shock carries enough energy to suggest that the star will be blown apart. Then it loses strength. Heavy nuclei absorb energy as they break into smaller components, and neutrinos carry energy away. The outward motion stalls inside the star. For a successful supernova, the shock must be revived. Current models indicate that neutrinos streaming from the hot, newly formed core deposit part of their energy behind the stalled shock. Turbulent flows help keep matter in that region long enough to absorb more heat. The details remain difficult to calculate because gravity, nuclear physics, radiation, and fluid motion all act at once. When the shock begins moving again, it tears through the surrounding layers. The star brightens in a supernova. Most of the original envelope is expelled into space, carrying oxygen, silicon, calcium, iron, and other elements into the interstellar medium. Those atoms may later enter new clouds, new stars, and new planets. The compact object left behind is only a few tens of kilometers across. Its formation releases more energy in neutrinos than in visible light. For several seconds, an enormous number of neutrinos escape from the collapsing core. They pass through the stellar material with little resistance and leave before the shock reaches the surface. In 1987, detectors on Earth recorded a small number of neutrinos from a supernova in the Large Magellanic Cloud. The signal lasted only seconds, yet it confirmed that core collapse and neutron-star formation follow the broad pattern predicted by theory. A neutron star is not born cold. Its interior begins at temperatures of tens of billions of degrees Celsius. Matter is so hot that trapped neutrinos influence its pressure and composition. During the first moments, the object is often called a proto-neutron star. It contracts as neutrinos escape, and the interior cools. Within tens of seconds, it settles toward the smaller, denser form associated with an ordinary neutron star. The final mass depends on the original star, the amount of material expelled, and the amount that falls back after the explosion. Some collapsing cores leave neutron stars. Others continue inward and form black holes. The boundary between those outcomes is not determined by the birth mass of the star alone. Rotation, mass loss, binary interaction, and the structure of the core all matter. The Crab Nebula preserves one of the clearest examples of what remains after a successful explosion. In the year 1054, observers in China recorded a new point of light in the sky. It was visible during the day for weeks and remained in the night sky for many months. The star itself had not appeared from nowhere. Its final explosion had made it briefly bright enough to be noticed across a large part of the world. Today, the expanding gas forms the Crab Nebula. Filaments of hydrogen, helium, oxygen, sulfur, and other elements spread outward from the explosion site. At the center sits a neutron star roughly 20 kilometers across, rotating about 30 times each second. The rotation is inherited. Before collapse, the stellar core turns far more slowly and occupies a much larger volume. As it contracts, angular momentum is conserved. The same broad effect causes a spinning skater to rotate faster when drawing in the arms. A core thousands of kilometers wide becomes an object the size of a city, and its rotation accelerates sharply. Magnetic fields are compressed as well. Field lines that once crossed a large stellar core are packed into a much smaller space. A typical neutron star can possess a magnetic field billions or trillions of times stronger than Earth's. Some objects, called magnetars, carry fields stronger still. The magnetic axis is not always aligned with the rotation axis. Charged particles move along the field lines and produce beams of radiation near the magnetic poles. As the star turns, those beams sweep across space. When one crosses Earth, telescopes record a pulse. The star is not turning its light on and off. The beam is moving. This lighthouse effect gives pulsars their regular rhythm. Some rotate several times each second. Others, especially recycled millisecond pulsars, spin hundreds of times each second. Their pulses can remain so stable that small irregularities reveal motion in a binary system, changes in the interstellar medium, or disturbances inside the star itself. The surface gravity is immense. A person could not stand there, and no ordinary material could preserve its shape. A loose object falling from a modest height would strike the surface at a significant fraction of the speed of light. Mountains cannot grow tall. On Earth, rock can support slopes and peaks kilometers high because gravity is comparatively weak. On a neutron star, even the strongest crust yields under far smaller differences in height. The surface may have rises measured in millimeters or centimeters rather than kilometers. Across a sphere the size of a city, it is extraordinarily smooth. Yet smooth does not mean featureless. Magnetic stresses can deform the crust. Hot regions can form where charged particles return to the surface. Accreted material from a companion can collect unevenly. Tiny distortions may matter because the star rotates so quickly. A slight asymmetry can produce gravitational waves, carrying away energy through small ripples in space-time. The density also changes the meaning of depth. Near the outer surface, atomic nuclei may still exist in a lattice. Deeper down, pressure forces more neutrons out of those nuclei. Lower still, the identity of individual nuclei fades. The material becomes a continuous nuclear medium whose exact behavior depends on interactions that are difficult to measure on Earth. The name neutron-star is therefore only partly accurate. Neutrons dominate much of the interior, but electrons and protons remain present. The outermost atmosphere may contain hydrogen or helium. The crust contains nuclei, arranged among mobile electrons. The inner regions may include superfluid neutrons, superconducting protons, hyperons, or deconfined quarks. Some of these components are supported by strong evidence. Others remain possible solutions allowed by current models. The star is a layered object. Its mass can exceed that of the Sun, yet its volume is smaller than that of many cities. A spoonful of its average density material would weigh far more than any mountain on Earth, although such material could not be removed and kept intact under ordinary conditions. Without the star's pressure, it would not remain in the same state. The escape speed near the surface is close to half the speed of light. Light itself can leave, but it loses energy while climbing out of the gravitational field. Its wavelength stretches toward the red. Time also passes at a different rate near the surface than it does far away. General relativity is not a small correction here. It shapes the object. The curvature of spacetime bends light around the star, allowing an observer to see more than half of the surface at once. A hot spot may remain visible after rotation carries it beyond the geometric edge. The pulse shape therefore contains information about compactness, the relationship between mass and radius. Later measurements use this bending to probe the material inside. The star cools quickly at first. Neutrinos carry energy from the interior, while photons leave from the surface. The crust and core may not begin at the same temperature, and it takes time for them to settle into thermal contact. Magnetic fields guide heat unevenly, creating warmer and cooler regions. The object also slows down. Radiation and particle winds carry away rotational energy. A young pulsar can power a surrounding nebula by feeding that lost energy into particles and magnetic fields. In the crab, the central neutron star drives a luminous bubble inside the expanding debris. The nebula shines not because the original explosion is still burning, but because the pulsar continues to supply energy. Over thousands and millions of years, the rotation becomes slower and the surface cooler. Some neutron stars fade from easy detection. Others remain visible because they accrete matter from a companion. Gas falling toward the compact star heats to high temperatures and releases X-rays. In some systems, the transferred material also spins the neutron star up again, producing a millisecond pulsar. A dead star can be made to rotate faster. The stability of the remnant depends on more than neutron degeneracy pressure alone. At nuclear density, the strong force between particles contributes substantially. Neutrons resist being confined to identical quantum states, but their interactions also shape the pressure. This is why the simple picture of a giant atomic nucleus is incomplete. A neutron star is held up by quantum statistics, nuclear forces, and the structure of space-time together. That combination can support only a limited range of masses. Too much mass, and no known pressure can maintain a stable neutron star indefinitely. Between the lower and upper limits lies a family of objects with different radii, rotation rates, magnetic fields, temperatures, and internal compositions. The surface gives only indirect hints. A thin atmosphere rests above a solid crust. Beneath it, nuclei grow heavier. neutrons begin to leak free, and matter takes shapes that do not occur in ordinary materials. The descent from the exterior to the core is measured in kilometers. But each kilometer crosses a different physical regime. The star appears small from space. Inside, it contains an entire sequence of matter. A neutron star's surface is not a clear boundary in the ordinary sense. Above the solid crust lies an atmosphere so thin that, on Earth, it would fit inside a small room. Depending on the star, that layer may contain hydrogen, helium, carbon, or heavier elements drawn from past accretion. Its thickness can be measured in centimeters, yet it shapes nearly all the light that escapes. Gravity presses the atmosphere downward with such force that density changes rapidly over a very short distance. Near the top, particles move through something resembling a hot gas. Lower down, pressure rises until the material behaves more like a condensed fluid. The transition happens without clouds, winds, or weather in any familiar form. There is simply less and less space between particles. The temperature may reach millions of degrees Celsius. At such temperatures, atoms are stripped of many or all of their electrons. Radiation passes through charged matter and is altered by magnetic fields that can be billions of times stronger than Earth's. The spectrum leaving the star carries traces of those interactions. A slight shift in energy can reveal composition, field strength, and the pull of gravity near the surface. The atmosphere is thin, but it is not unimportant. It acts as the last filter between the interior and space. Beneath it lies the outer crust. Here, atomic nuclei settle into a lattice surrounded by a sea of electrons. The arrangement has some resemblance to a metal, though the density is far beyond anything found in a laboratory. The nuclei are not ordinary atoms because their electrons are no longer attached to individual centers. They move through the material as a shared population. With increasing depth, pressure pushes the electrons to higher energies. Some are captured by protons inside nuclei, turning them into neutrons. The nuclei become richer in neutrons and less like the stable elements found on Earth. Their shapes remain roughly spherical at first, but their composition moves steadily away from familiar matter. The crust may be solid, yet it is not perfectly rigid. It can bend under stress. It can store energy from changes in the magnetic field or from small differences between the rotation of the crust and the motion of material below. For long periods, the strain remains hidden. Then, a region shifts. On a magnetar, the result may be a starquake. The movement can alter the magnetic field and release a burst of X-rays or gamma rays. The crust does not crack in the same way as rock. At these pressures, matter deforms through processes governed by nuclear forces and quantum mechanics. The word quake is an analogy, useful because the surface changes suddenly, but the material taking part has no true earthly counterpart. Even a small adjustment can affect the whole star. A change measured in centimeters may alter the rotation rate or redirect heat moving through the crust. The scale of the object makes tiny distortions meaningful. The outer crust extends only a few hundred meters. Density rises until a threshold called neutron drip is reached. Beyond that point, nuclei can no longer contain all of their neutrons. Some begin to leak out and move between the nuclei while the lattice remains. This marks the beginning of the inner crust. In an isolated neutron star, the crust preserves material produced during the original collapse. In an accreting system, the outer layers can be rebuilt. Gas from a companion settles onto the surface, is buried, and passes through a sequence of reactions as pressure increases. Electrons are captured, neutrons are released. At greater depth, nuclei can fuse, even when temperature alone would not normally be sufficient. These reactions are driven mainly by density. The nuclei are confined so closely that quantum tunneling allows them to join. The process is sometimes called pyknonuclear fusion, meaning fusion produced by extreme compression. It releases heat inside the crust and changes the nuclei that continue downward. An accreted crust may therefore differ from the original crust in composition and impurity. Those differences alter electrical conductivity, thermal transport, and the way magnetic fields evolve. They also affect how quickly the surface responds after an accretion episode ends. The crust does not preserve a simple geological record. Material is continually transformed as it sinks. A nucleus created near the surface may capture electrons several times, shed neutrons, merge with another nucleus, and finally disappear into uniform matter. The descent is chemical only in its earliest stages. Lower down, it becomes a sequence of nuclear rearrangements. The phrase neutron drip sounds gradual, and on the scale of the star it is. There is no sharp waterfall of particles. Instead, the balance between nuclear binding and pressure changes with depth. Neutrons that were once confined become energetically able to exist outside the nuclei. A background of free neutrons appears and grows denser lower down. Many of those neutrons are expected to form a superfluid. In a superfluid, particles move in a coordinated quantum state with extremely low resistance. The flow is not simply frictionless liquid in the ordinary sense. Rotation occurs through narrow vortices, each one carrying a fixed amount of circulation. These vortices may attach to structures in the crust and remain pinned there for years. The electrons continue to move through the lattice, carrying heat and electric current. Magnetic fields guide their paths. In some regions, heat travels more readily along field lines than across them. The surface temperature can therefore become uneven, even when the deeper interior is closer to uniform. The crust is also where matter begins to lose its preference for simple shapes. At lower density, nuclei tend to be round because surface tension pulls them inward. Pressure from surrounding particles works against that tendency. Deeper in the star, the competition changes. Nuclei can stretch, join, flatten, and merge into extended structures. Physicists refer to this predicted material as nuclear pasta. The name is informal, but the underlying calculations are serious. Computer models follow large numbers of protons and neutrons interacting under high pressure. Depending on density and temperature, the lowest energy arrangement may resemble isolated spheres, long cylinders, flat sheets, tubes, or bubbles. Round clusters are sometimes called gnocchi. Long rods become spaghetti. Flat sheets are compared with lasagna. The labels make the shapes easier to remember, though the structures themselves may be less orderly than the names suggest. Defects, branching regions, and mixed forms can appear. These shapes arise because two tendencies are competing. The strong nuclear force draws nearby protons and neutrons together. Electric repulsion pushes protons apart. At lower density, small nuclei provide a workable compromise. At higher density, larger connected forms may reduce the total energy of the material. The result may be stronger than any known substance under ordinary conditions. Simulations suggest that nuclear pasta can withstand enormous stress before changing shape. Its strength does not come from chemical bonds. It comes from the collective behavior of nuclear matter. The layer is thin compared with the star, perhaps a few hundred meters or less. Its mass can still exceed that of many planets. No telescope has photographed nuclear pasta. No sample can be removed. Its existence is inferred from theory, simulations, and the need to understand observations that depend on crust behavior. The uncertainty matters. Different models predict different thicknesses, shapes, and transport properties. Some clues may come from cooling. When a neutron star in a binary system pulls gas from a companion, the incoming material strikes the surface and is buried by later arrivals. Nuclear reactions occur deeper in the crust, releasing heat. If accretion stops, astronomers can watch the crust cool back toward the temperature of the core. The cooling curve depends on how easily heat moves through each layer. A highly ordered crust conducts heat differently from one filled with impurities and defects. Nuclear pasta near the base may slow heat flow if its structures scatter electrons strongly. Repeated X-ray observations can therefore test aspects of the crust without seeing it directly. Other clues come from rotation. A perfectly symmetric spinning star would not produce a continuous gravitational wave signal. A slight mountain, density imbalance, or internal strain can change that. The deformation may be extremely small compared with the star's radius. Still, rapid rotation repeats the asymmetry hundreds of times each second, creating a persistent disturbance in spacetime. Detectors have not yet confirmed continuous gravitational waves from an individual neutron star. The upper limits are already useful. They constrain how large a deformation can be and how much stress the crust can support. A stronger crust permits a larger mountain. A weaker one yields sooner. The smoothest objects in the universe may therefore carry mountains that are almost invisible, yet large enough to matter for gravitational wave astronomy. Magnetic fields provide another source of stress. In an ordinary pulsar, the field may evolve slowly over millions of years. In a magnetar, the field stores far more energy and can twist the crust from below. Currents move through both solid and fluid regions. As the field rearranges, surface hotspots can shift and bursts can occur. The crust also influences how those bursts unfold. Some energy travels through the star as vibrations. Certain oscillations may briefly modulate the X-ray light after a giant magnetar flare. Researchers have proposed that these signals could reveal the thickness and composition of the crust, much as seismic waves reveal layers inside Earth. The interpretation is difficult. Magnetic fields couple the crust to the fluid core, so a vibration may not remain confined to one region. Different modes overlap. The observed frequencies may reflect the entire star rather than a single layer. The signals remain valuable, but the mapping from frequency to structure is not simple. At the bottom of the inner crust, the distinction between nuclei and surrounding neutrons begins to fade. The rods and sheets grow closer, their boundaries soften. Eventually, the material becomes nearly uniform nuclear matter. The crust ends. Only about 1 kilometer has been crossed, but several forms of matter have already appeared. A thin atmosphere gives way to an electron-rich lattice. Neutrons leak free. Superfluid motion develops. Nuclei stretch into extended forms before dissolving into the material below. The pressure at this depth is enormous, yet the crust is still only the outer shell. Most of the star's mass lies deeper. The next region is often called the outer core. Here, individual nuclei no longer survive. Neutrons dominate, with a smaller population of protons, electrons, and perhaps muons. The material behaves as a collection of interpenetrating fluids rather than a single simple substance. The crust leaves traces in everything above it. The heat that reaches the surface, the timing of pulses, the afterglow of accretion, the possibility of starquakes, and the faint chance of continuous gravitational waves. It is thin enough to disappear in a diagram drawn without care. Physically, it is the transition between atoms and something denser. Below it, the idea of a solid surface no longer helps. Matter flows, pairs, and rearranges under pressures that continue to rise. The star becomes less visible with every step inward. A neutron star cannot be opened, sampled, or placed beneath a microscope. Its surface lies thousands of light-years away, and the material below that surface exists under pressures that cannot be reproduced in any laboratory. Yet mass and radius still leave a signature in light. The signature is small, repeated, and shaped by gravity. NICER was built to read it. The neutron star Interior Composition Explorer is attached to the outside of the International Space Station. It does not take pictures in the ordinary sense. Instead, it records the arrival times and energies of individual X-ray photons. For a bright millisecond pulsar, those photons arrive in a rhythm tied to the star's rotation. Millions of arrivals are gathered, aligned, and folded together until a pulse shape appears. That pulse shape contains more than timing. A millisecond pulsar is an old neutron star that has been spun up by matter transferred from a companion. Its rotation can remain stable for long periods. Some turn hundreds of times each second. The surface is not equally bright everywhere. Small regions near the magnetic poles can be heated by charged particles returning along magnetic field lines. These hot regions emit thermal X-rays. As the star rotates, a hot region moves toward the observer, crosses the visible face, and turns away. Its light rises and falls. If space around the star were flat, the shape of that rise and fall would depend mostly on the size and location of the hot region. Near a neutron star, space is not flat. Gravity bends the path of the escaping photons. This bending changes what can be seen. A sufficiently compact star reveals part of the hemisphere that would normally lie beyond the edge. A hot region can remain visible even after rotation carries it around the far side. The pulse becomes smoother because the light never disappears as completely as it would around a less compact object. Compactness means mass divided by radius. A star with a large mass and a small radius bends light more strongly than a star with the same mass and a larger radius. By modeling the pulse, researchers can estimate which combinations of mass, radius, surface geometry, and viewing angle are consistent with the data. The method is called pulse profile modeling. The calculation follows photons from the surface through curved spacetime to the detector. It includes the star's rapid rotation, which changes photon energies through the Doppler effect. It includes the slight flattening produced by that rotation. It also includes the way a thin atmosphere directs radiation differently from a perfect, glowing surface. Each detail changes the pulse by a small amount. Together, they create a pattern precise enough to carry information about the star's size. The first major NICER radius result came from pulsar, J30 plus 0451. This nearby millisecond pulsar turns a little more than 200 times each second. Its X-ray pulse could not be explained by two simple, matching circles placed at opposite magnetic poles. The heated regions appeared more complicated and were concentrated on the same broad side of the star. The result altered the usual textbook picture. A dipole magnet is often drawn with one pole in the north and one in the south. The pulse from J30 instead suggested a surface field with several components. One warm region could be compact. Another could stretch into a crescent or arc. Different teams used different descriptions, yet both found a radius near 13 kilometers. The surface map was uncertain. The broad size was not arbitrary. This is an important distinction. NICER does not observe the core. It measures light from the surface and compares that light with many possible models. A radius estimate emerges only after uncertainty in the hot regions, atmosphere, background, mass, distance, and viewing geometry has been carried through the analysis. No single photon gives the answer. The answer comes from the population. PSR J 740 plus 6,620 provided a different test. Radio observations of its orbit around a white dwarf had already shown that it carries a little more than twice the mass of the Sunday. It is among the heaviest neutron stars with a reliable mass measurement. More mass normally means stronger gravity and a greater tendency to compress the material. A very soft equation of state would allow such a heavy star to become much smaller than a lighter one. A stiffer equation of state would preserve a larger radius. NICER observed the X-ray pulses from J740, while XMM Newton helped measure background emission and the total X-ray spectrum. The inferred radius was not sharply smaller than the radius of J30. Although J740 holds far more mass, the two stars are broadly similar in size. The interior must resist compression strongly enough to support that result. This does not identify a single substance in the core. Several equations of state remain possible. It does rule against models that become too soft at the densities reached inside a heavy neutron star. Any proposed material must produce enough pressure to support more than two solar masses while remaining compatible with the measured radius. The observation turns a geometric quantity into a test of nuclear physics. PSR J 437 4715 adds another point to the map. It is one of the nearest and brightest millisecond pulsars, about 500 light-years away, and rotates roughly 174 times each second. Long radio observations have constrained its mass and viewing geometry. NICER's result, reported in 2024, gave an equatorial radius near 11.4 kilometers, with an uncertainty of several percent. The measurement was the most precise NICER radius estimate at the time. It lies somewhat below some earlier expectations, though it remains statistically consistent with the broader set of NICER results. 3 measured stars do not form a complete mass-radius curve. They begin to mark its shape. The curve is one of the clearest ways to distinguish equations of state. For each possible description of dense matter, the equations of stellar structure predict how radius changes as mass increases. Some models produce stars that remain nearly the same size across a wide range of masses. Others predict a faster contraction. A strong phase transition in the core can create an abrupt bend, or even a separate family of stable stars. Measurements at different masses are therefore more useful than repeated measurements of nearly identical objects. A lighter star samples one range of central density. A star near 2 solar masses reaches deeper conditions. Together, they test how matter responds as pressure rises. The relationship is not read from radius alone. Radio timing can measure mass in certain binary systems through effects predicted by general relativity. Gravitational wave observations constrain how easily neutron stars deform during an inspiral. X-ray spectroscopy can provide information about temperature and surface emission. Nuclear experiments on Earth test the behavior of neutron-rich matter at lower densities. Each measurement touches a different region of the same problem. Their overlap narrows the possibilities. Pulse profile modeling also exposes the difficulty of converting light into geometry. Radiation does not leave every surface element equally in every direction. Different atmospheres produce different spectra and beaming patterns, while strong magnetic fields can alter them further. Background light matters as well. NICER does not form an image. It records photons from the pulsar alongside diffuse sky emission and instrumental background. Statistical models must separate those components. The shape of the hot regions remains another source of uncertainty. A simple circular cap may fit one pulsar and fail for another. The magnetic field at the surface can include dipole, quadrupole, and higher-order structures. Return currents can heat narrow arcs, rings, or separated patches. Even the star's rapid rotation must be handled carefully. Rotation changes the apparent brightness of the approaching and receding sides. It shifts photon energies. It also makes the equator extend slightly farther than the poles. For the fastest pulsars, treating the object as a perfect sphere would distort the inferred radius. The model must be evaluated many times. Each trial chooses a mass, radius, hot region geometry, atmosphere, orientation, and background. Relativistic ray tracing predicts a pulse, which is compared with the observed photons. Poor combinations are rejected. Better ones remain with a statistical weight. The result is a probability distribution, not a ruler reading. That caution gives the measurement its value. Dense matter cannot be understood through a single best number stripped of uncertainty. The full range shows which equations of state remain compatible with observation and which begin to fail. Light bending provides the central clue. If the star were less compact, a hot region would vanish more completely behind the limb, producing a deeper minimum in the pulse. If it were more compact, the far side would remain more visible, flattening the modulation. Radius is written into the amount of disappearance. The same gravity that hides the interior makes the measurement possible. There is another quiet result in the pulse shapes. They show that neutron star surfaces are not simple maps of two opposite magnetic poles. J30 required complex heated regions. J740 appears closer to a two-spot arrangement, though its geometry is still modeled rather than photographed. J437 adds its own pattern. The stars share the same broad class, but not the same surface. Their magnetic histories differ. Accretion may have buried or rearranged fields. Currents in the crust may have moved. Rotation and cooling may have altered the pathways along which particles return. A radius study, therefore, also becomes a study of magnetic topology. The interior remains inaccessible, but its pressure shapes the radius. The radius shapes the bending of light. The bending shapes the pulse. That sequence carries information from matter several kilometers below the surface to an X-ray detector in low Earth orbit. Nothing is removed from the star. Only the timing of light is collected. As more pulsars are measured, the separate probability bands begin to overlap. A model that fits one mass may fail at another. A proposed phase transition may predict a radius change that does not appear. A stiff model may support heavy stars, but produce radii that are too large. A soft model may fit a smaller star, but collapse before reaching two solar masses. The allowed region becomes narrower. NICER cannot finish the problem alone. Its estimates depend on atmosphere models, background estimates, and independent mass measurements. Future X-ray missions may collect larger photon samples. Radio timing will refine masses, while gravitational wave detectors add information from stars in their final orbits. The measurements already change the way the interior is discussed. A neutron star is no longer represented only by a theoretical mass and an assumed radius. Several objects now occupy measured regions on the mass-radius plane. Each region is broad. Together, they form a boundary. The light from a hot patch may travel for centuries before reaching the solar system. It then strikes a detector for a fraction of a second, one arrival among millions. When those arrivals are placed in order, the surface begins to rotate on the page. Gravity appears in the curve. The radius follows. Below that measured surface, matter is moving in ways that light cannot show directly. Some of it may flow without ordinary friction. Some may carry rotation in narrow quantum vortices. The next clue does not come from the shape of a pulse, but from the moment the pulse unexpectedly shifts. A pulsar can keep time with a regularity that seems almost mechanical. Each rotation carries a beam of radiation across space, and each crossing appears at a telescope as another pulse. Over months and years, the intervals change only gradually. The star loses rotational energy, so the pulses arrive a little farther apart. The slowing is steady enough to predict far into the future. Then, without warning, the rhythm shifts. A pulse arrives slightly earlier than expected. The next one does the same. The star has begun rotating faster, though no matter has fallen onto it, and no external hand has pushed it. The change may be only a few parts in a billion, but the timing is precise enough to reveal it. Astronomers call the event a glitch. The name sounds small. Inside the star, it may involve a rearrangement of matter across kilometers. An ordinary rotating liquid can slow continuously. Every part can adjust its motion by tiny amounts, passing angular momentum through viscosity and friction. A superfluid behaves differently. Its rotation is carried by narrow quantum vortices, each containing a fixed amount of circulation. The fluid cannot choose any rotational state it likes. It changes by altering the number and arrangement of those vortices. Neutrons in the inner crust are expected to form such a superfluid. They pair through the attractive part of the nuclear force, much as electrons pair in a terrestrial superconductor. The pairs no longer behave as isolated particles. They enter a shared quantum state that can flow with extremely little internal resistance. The crust around them is slowing because the star radiates energy. The superfluid does not always slow at the same rate. Its vortices must move outward for the fluid to reduce its rotation. In the inner crust, those vortices pass through a lattice of neutron-rich nuclei. Interactions between the vortices and the lattice can hold them in place. This is called pinning. While the crust loses angular momentum, part of the superfluid keeps rotating more quickly. A difference builds between the two. The star can preserve that difference for years. The faster superfluid becomes a hidden reservoir of angular momentum beneath the surface. Stress grows on the pinned vortices as they are pulled away from the positions preferred by the slowing crust. Eventually, some break free. One unpinning event may disturb nearby vortices. A small movement can spread through the network, allowing many vortices to travel outward over a short time. Angular momentum passes from the superfluid to the crust. The observable surface spins up, and the pulses shift. The change can happen between one observation and the next. Vela is one of the best-known glitching pulsars. It is young, turns about 11 times each second, and experiences relatively large glitches every few years. The jumps are small compared with its total rotation, yet much larger than the timing noise around them. After each event, part of the increase remains, while another part slowly relaxes. That recovery is as informative as the jump itself. Different regions inside the star do not couple to the crust at the same speed. Some respond almost immediately. Others exchange angular momentum over days, months, or longer. By following the pulse frequency after a glitch, researchers estimate how much of the interior took part and how strongly its components interact. The result is not a simple picture of one fluid inside one shell. Several reservoirs may be present. The neutron superfluid in the crust is the most familiar candidate, but it may not hold enough angular momentum to explain every large glitch by itself. Neutrons moving through a lattice are not entirely independent of that lattice. A quantum effect called entrainment causes part of their motion to be linked to the crustal structure. This reduces the freely available reservoir. If entrainment is strong, some angular momentum may need to come from the core. The outer core is expected to contain mostly neutrons, with a smaller number of protons, electrons, and muons. Neutrons may be superfluid there as well. Protons may form a superconductor, allowing electric current to persist with little resistance. A rotating neutron superfluid contains vortices. A proton superconductor can contain narrow tubes of magnetic flux. Their interaction may determine how quickly the core follows changes in the crust. Vortices can cut through flux tubes, drag them, or become temporarily attached. Each possibility produces a different form of internal friction. The details are still unsettled. This uncertainty is useful rather than empty. Glitches turn invisible coupling into a measurable change in time. The rise of the glitch, the size of the jump, and the long recovery each test a different part of the model. Some glitches may rise in less than a minute. Observations of Vela have placed strong limits on how slowly the transfer can occur. A rapid rise suggests that at least part of the reservoir is connected efficiently to the crust once vortices begin moving. A slower recovery then reveals regions that remain weakly coupled. Not every pulsar glitches in the same way. Young pulsars often show sudden jumps and complex recoveries. Older millisecond pulsars are usually more stable, though they are not perfectly silent. Some objects show many small irregularities. Others produce rare, large events. The diversity may reflect temperature, magnetic field, crustal structure, and the amount of superfluid available. A warmer interior allows vortices to move through thermal activation more easily. In a cooler star, pinning may hold them for longer. Stronger magnetic fields can alter the coupling between charged and neutral components. The age printed on a pulsar catalog does not reveal all of this. Two stars with similar spin periods can have different internal histories. Crustquakes were once considered a complete explanation for glitches. As a star slows, its equilibrium shape becomes less flattened. A solid crust resists the change, stores strain, and eventually shifts. That adjustment can reduce the moment of inertia and increase the rotation rate, rather like a skater drawing mass inward. Crustal movement may contribute in some events, especially when magnetic stress is present. For the repeated large like Vela, however, superfluid angular momentum transfer provides the stronger general explanation. The crust can trigger the release without supplying most of the angular momentum itself. The distinction matters. A quake changes the container. A superfluid glitch changes how hidden motion is shared with it. There are also events that move in the opposite direction. An anti-glitch is an abrupt decrease in observed rotation frequency. Such events have been reported mainly in magnetars and accreting systems, where changes in magnetic torque or surrounding matter can alter the spin. PSR B54069 made the subject less tidy. This young, rotation-powered pulsar lies in the Large Magellanic Cloud. It turns roughly 20 times each second and resembles the Crab pulsar in age and energy loss. Nicer observations covering an event in 2023 were analyzed in a study released in 2024. The first interpretation described a small, permanent decrease in rotation frequency without a major X-ray burst or a clear change in the pulse profile. That would make it the first radiatively quiet anti-glitch reported in a rotation-powered pulsar. An internal explanation was proposed. A change in the superfluid component could increase the moment of inertia of the normally rotating part of the star, causing the observed crust to slow. The event was small, and the mechanism remained tentative. Later analysis offered another reading of the same interval. Instead of a permanent step in frequency, the data could be described as a temporary swing in the spin-down rate lasting about 2 months. In that model, the star did not make a single clean backward jump. Its braking changed for a time and then returned toward its previous behavior. The later work found this interpretation statistically favored. The difference shows why pulsar timing requires long baselines. A sudden step, a short recovery, and a temporary change in torque can produce similar pulse arrivals over a limited span. More observations before and after the event help separate them. Whether the B540 event is ultimately classified as an anti-glitch or a spin-down swing, it remains a clue. A rotation-powered pulsar changed its timing without an obvious bright outburst. The cause could lie in the magnetosphere, the interior, or a coupling between both. The surface and the core are not separate clocks. Magnetic fields thread the crust and extend into space. Charged particles fill the magnetosphere and carry away angular momentum. A change in those currents alters the external braking torque. At the same time, superfluid vortices and superconducting flux tubes control how the interior follows the crust. Similar timing signatures can therefore emerge from very different places. Pulse shape and brightness can help distinguish them. A radiative change accompanying a timing event points toward the magnetosphere, though the absence of such a change does not prove an internal origin. Some external rearrangements may be faint. Some internal events may disturb the magnetic field enough to affect emission. The evidence arrives in pieces. Glitches also reveal the amount of matter involved. If a jump transfers a known fraction of the star's angular momentum, the hidden reservoir must contain at least that much moment of inertia. Repeated glitches over decades provide a longer accounting. The total angular momentum restored in jumps must be stored between them. This calculation links timing to the thickness of the crust and the equation of state. A star with a thicker inner crust can contain a larger crustal superfluid reservoir. A more compact star may have a smaller fraction of its moment of inertia in the crust. If quake nmat. Crust has applied, the core must participate, or the microphysics of entrainment must differ from current estimates. The same pulses used to measure radius can therefore test superfluidity. A radius tells how compressed the whole object is. A glitch tells how its internal components exchange motion. Cooling reveals how energy leaves. No single measurement describes the star completely, but their constraints intersect. Superfluidity also changes heat capacity and neutrino emission. When neutrons pair, the available states for ordinary scattering are altered. Cooling can slow in some regimes, while the formation and breaking of pairs can create additional neutrinos in others. The timing behavior and thermal history are connected by the same microscopic interactions. On Earth, superfluids are created at very low temperatures. Inside a neutron star, the absolute temperature may still be millions of degrees, relative to the enormous Fermi energy of the particles that is cold enough for pairing. The word cold takes on a different meaning in dense matter. The superfluid is not a quiet underground ocean. It is crossed by vortices, coupled to a lattice, threaded by magnetic structures, and changing as the star cools. Its motion is constrained by quantum rules across a region measured in kilometers. A glitch brings a fraction of that motion to the surface. The pulse arrives early. Telescopes record the shift, Days and years of recovery follow. From those small changes, the interior begins to separate into components: a crust that can store strain, a superfluid that can preserve faster rotation, and a core whose coupling remains partly hidden. Deeper still, the particles themselves may change. Neutrons and protons may no longer be the only stable inhabitants. At the highest pressures, the question is no longer only how matter moves, but what matter has become. The outer core begins where the crust has lost its separate nuclei. Matter is no longer arranged into a lattice. Neutrons form most of the fluid, while smaller populations of protons, electrons, and muons move through the same volume. Each component follows its own quantum rules, yet all of them contribute to the pressure that keeps the star from contracting. This description is already less simple than the name neutron-star suggests. The proportions are set by a slow balance of reactions. A neutron can transform into a proton, an electron, and an antineutrino. A proton and an electron can combine and return to a neutron, releasing a neutrino. In an old, cool star, these reactions settle toward beta equilibrium, a condition in which neither direction is strongly favored. Charge must also balance. The number of positively charged protons is matched by negatively charged electrons, and, deeper down, muons. Pressure changes that balance with depth. As particles are packed more closely, the highest occupied energy levels rise. A new particle species can appear when creating it becomes less costly than forcing the existing particles into still higher energies. The interior may therefore change composition without any sudden addition of material from outside. The star rearranges what is already there. Near the outer core, neutrons and protons remain recognizable as the same broad particles found in atomic nuclei. Together they are called nucleons. Their interactions are governed by the strong force, which attracts at some distances and resists compression at shorter distances. The exact behavior of that force in dense, neutron-rich matter is not fully measured. Laboratories can collide nuclei and study short-lived fragments. Those experiments test matter near and somewhat above ordinary nuclear density. The center of a heavy neutron star may reach several times that density while remaining cold enough to behave very differently from the hot matter created in a collision. The conditions overlap only partly. Theory must bridge the remaining distance. At lower densities, calculations begin with neutrons and protons interacting through forces constrained by nuclear experiments. At very high densities, quantum chromodynamics describes matter in terms of quarks and gluons. Between those limits lies the region most relevant to neutron star cores, where direct calculations become difficult and many equations of state remain possible. One option is that nucleons persist all the way to the center. They may change their interactions as density rises, but they remain intact. A sufficiently repulsive component of the nuclear force can make the equation of state stiff enough to support stars heavier than twice the mass of the Sunday. This is the conservative picture. It is not the only one. Neutrons and protons belong to a larger family of particles called baryons. Each baryon is built from 3 quarks. Protons contain 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. Under greater pressure, baryons containing strange quarks may become energetically possible. These particles are called hyperons. A lambda hyperon, for example, contains 1 up quark, 1 down quark, and 1 strange quark. It is heavier than a neutron in empty space and decays quickly under ordinary conditions. Inside dense matter, the comparison changes. Existing neutrons occupy increasingly energetic states. At some point, replacing a high-energy neutron with a heavier hyperon in a lower available state may reduce the total energy. If that threshold is crossed, hyperons begin to appear. Their presence gives the particles more ways to share density. That usually lowers the pressure at a given energy density. The equation of state becomes softer, and the maximum mass predicted for the star falls. Here, the models meet an observation that cannot be ignored. Several neutron stars have measured masses close to or above twice the mass of the Sunday. any proposed composition must support them. Many early hyperon models could not. This conflict is known as the hyperon puzzle. The puzzle does not prove that hyperons are absent. It shows that a simple treatment of them is incomplete. Repulsive forces between hyperons and other baryons may become stronger at high density. Three-particle interactions may add pressure. The threshold for hyperon formation may lie deeper than older calculations assumed. Some recent models delay their appearance or reduce their abundance enough to preserve a heavy star. The central uncertainty is interaction strength. Hyperons are difficult to study because they decay quickly, and experimental data on hyperon-rich matter are limited. A small change in the assumed forces can move their threshold or alter the maximum mass substantially. The particles are known. Their behavior inside a neutron star is not. A deeper change may occur if nucleons cease to remain intact. Quarks are normally confined inside baryons. Pulling one quark away does not reveal an isolated particle. The energy stored in the strong field grows until new quark-antiquark pairs form. In ordinary conditions, confinement prevents free quarks from traveling through matter on their own. At sufficiently high density, the boundaries of neighboring baryons may overlap. Quarks could then move through a larger volume rather than remaining assigned to individual neutrons or protons. This state is called deconfined quark matter. The word deconfined can suggest particles drifting independently. The likely reality is more organized. Quarks still interact strongly. At the low temperatures expected in an old neutron star core, they may pair and form color superconducting phases. Different combinations of up, down, and strange quarks can produce several candidate states. None has been observed directly. A transition to quark matter could happen gradually through a crossover in which the description changes without a sharp boundary. It could also occur as a first-order phase transition, where density jumps across an interface. The form depends on the strong interaction and on how electric charge is distributed between the phases. A strong transition would leave structural consequences. As the central pressure increases, a small quark core might appear. With more mass, the core could grow. In some equations of state, the transition destabilizes the star. In others, stability returns at a smaller radius, creating a second branch of compact objects with masses similar to ordinary neutron stars, but different internal compositions. These hypothetical pairs are sometimes called twin stars. Two stars could then carry nearly the same mass while having noticeably different radii. One would contain mostly hadronic matter, meaning matter built from baryons. The other would hold a large quark core. A precise set of mass and radius measurements might reveal the split. No confirmed twin star pair is known. Present measurements are still too broad to establish such a branch. Quark matter does not automatically make a star too soft. Early descriptions often assumed that deconfinement would reduce pressure sharply. Modern models allow stronger quark interactions, and some produce enough pressure to support heavy neutron stars. The transition can soften the material over one density range and stiffen it again deeper inside. This is one reason a large radius does not settle the composition by itself. Different microscopic models can produce similar mass-radius curves. A nucleonic star and a hybrid star with a quark core may occupy nearly the same region on the diagram. The same exterior can hide different interiors. Researchers therefore combine several kinds of evidence. A measured mass above two solar masses sets a lower bound on the pressure at high density. Radius estimates constrain pressure at somewhat lower densities. Gravitational waves from a binary inspiral reveal tidal deformability, which measures how readily each star changes shape in the gravitational field of its companion. Cooling adds another test. Some compositions allow rapid neutrino-producing reactions. If the proton fraction becomes high enough, a direct Urca process can operate, allowing neutrons and protons to transform efficiently and carry energy away through neutrinos. Hyperons, or quarks, can open additional cooling channels. A star that cools too quickly for its age may point toward one of these processes. A warm star of the same age can rule against models in which rapid cooling begins too easily. Pairing gaps, crust composition, magnetic fields, and uncertain ages complicate the comparison, so temperature alone cannot identify the core. Each clue narrows a different part of the problem. Theoretical models must also connect smoothly to known physics. At densities near the crust, they must agree with nuclear experiments and many-body calculations. At extremely high density, they should approach results from quantum chromodynamics, where the interaction becomes more manageable through perturbative methods. A proposed equation of state cannot simply be adjusted at one density without affecting the rest. Between the two ends, freedom remains. Recent analyses have found that equations of state compatible with current observations often show behavior associated with deconfined matter in the cores of the heaviest stars. This is evidence from inference, not detection. It means that quark-like behavior can provide a natural fit to the allowed pressure and density relationships. It does not mean that a telescope has observed quarks inside a specific star. Other analyses retain fully hadronic cores and also satisfy the data. The honest result is a range, not a verdict. Even the word core can hide several layers. A star of moderate mass may never reach the threshold for hyperons or quarks. A heavier star may contain a small region of new matter. A star close to its maximum stable mass could reach conditions not present in most of the neutron star population. There may be no universal interior shared by every object. The central density depends on mass and on the equation of state itself. A stiffer star can support a given mass at a lower central density. A softer one compresses further. Two stars with the same mass but different microscopic physics may therefore place their deepest matter in different regimes. This creates a circular difficulty. Composition determines the equation of state. The equation of state determines the density profile. The density profile determines which particles are allowed to appear. Observations break the circle slowly. A heavy pulsar proves that the equation of state cannot remain too soft. A radius measurement constrains the star's compactness. A merger tests deformability. A cooling curve limits the available neutrino reactions. None of these shows the core directly, but together they reduce the space in which it can hide. The possible inhabitants can be listed: nucleons, hyperons, meson condensates, and deconfined quarks. The list is not a map. Their thresholds depend on interactions that remain uncertain, and more than one form may coexist. At the center, pressure reaches its highest value. Particles occupy every low-energy state available to them. New degrees of freedom can lower the energy, then alter the pressure supporting the layers above. A change too small to see locally can shift the radius of the whole star or lower the greatest mass it can bear. The core remains dark, not because it emits no information, but because every message is indirect. Its composition is written faintly into mass, radius, temperature, rotation, and the shape of gravitational waves. Those signals do not yet spell a single answer. They draw boundaries around the possibilities. One boundary matters more than all the others. Whatever the core contains, there is a greatest mass for which its pressure can still balance gravity. Beyond that point, the question of composition becomes the question of survival. A neutron star can carry more mass than the Sun, while remaining only a few tens of kilometers wide. The pressure inside rises with every added layer, and the central material is forced into states that no laboratory can hold for more than an instant. For a time, the star answers gravity with quantum pressure and nuclear forces. That answer has a limit. The limit is usually named after Richard Tolman, J. Robert Oppenheimer, and George Volkoff. In the late 1930s, their work joined general relativity to a model of matter under pressure and asked how a spherical star could remain in equilibrium. The resulting equations describe how pressure must change from the center to the surface when gravity is strong enough to curve space-time. For an ordinary star, Newtonian gravity often gives a useful approximation. For a neutron star, it does not. Pressure itself contributes to gravity. Energy density contributes as well. The deeper layers are not merely supporting the weight above them. Their own pressure strengthens the gravitational field they are trying to resist. This makes the final balance unusually delicate. The Tolman-Oppenheimer-Volkoff limit, often shortened to the TOV limit, is the greatest mass a cold, non-rotating neutron star can support for a particular equation of state. It is not one universal number known in advance. Change the microscopic behavior of dense matter, and the maximum mass changes with it. A soft equation of state allows matter to compress more easily. The star becomes smaller, the central density rises quickly, and stability may end at a lower mass. A stiff equation of state produces greater pressure at the same density and can support a heavier star. Observations already set a firm requirement. Several pulsars carry masses close to or above twice the mass of the Sunday. Any equation of state that collapses before reaching those masses cannot describe the real population of neutron stars. The upper boundary is harder to determine. Current combinations of pulsar masses, X-ray radii, gravitational waves, and nuclear theory place it within a limited range, but the exact value remains uncertain. The most massive, stable, non-rotating star may lie only modestly above the heaviest pulsars already known. The boundary also appears in the mathematics of equilibrium sequences. Imagine calculating a series of stars with the same equation of state, but steadily increasing central density. Their masses rise at first. Eventually, the sequence reaches a turning point. Beyond it, adding central density no longer produces a heavier, stable star. A small radial disturbance grows instead of settling, and the configuration moves toward collapse. The maximum mass is therefore not simply where pressure disappears. It is where the available pressure can no longer restore the star after even a slight compression. The TOV limit applies to an idealized object that does not rotate. Real neutron stars almost always turn. Rotation provides additional support. Matter near the equator carries angular momentum and resists being drawn directly inward. A uniformly rotating star can therefore remain stable at a mass above the non-rotating maximum. Near the fastest possible rotation, the increase is commonly around 1/5, though the precise amount depends on the equation of state. There is another limit there. Spin cannot rise without end. At the mass-shedding boundary, material at the equator moves so quickly that any further increase would allow it to escape. A star near this boundary is flattened, wider around the equator than from pole to pole. A neutron star above the TOV limit but below the maximum allowed by uniform rotation is called supermassive. It survives because it spins. As radiation and magnetic torques remove angular momentum, the extra support gradually weakens. Once the rotation falls below the rate required for stability, collapse can occur even if no new mass has been added. The star crosses the boundary by slowing down. A different object can form after two neutron stars merge. The remnant is hot, rapidly rotating, and deeply disturbed. Its inner regions may rotate at different speeds. This differential rotation can support more mass than uniform rotation can. Thermal pressure also contributes for a time. If the remnant exceeds the uniformly rotating maximum but remains temporarily supported by differential rotation and heat, it is called hypermassive. The distinction is important. A supermassive star may survive for a long time while spinning down. A hypermassive remnant is expected to be much more temporary. Its support is being erased from within. Magnetic fields connect regions rotating at different rates. Turbulence redistributes angular momentum. Neutrinos carry heat away. Gravitational waves remove energy and angular momentum. As the remnant becomes more uniform and cooler, the extra support declines. The time before collapse can range from almost immediate to much longer intervals, depending on total mass and the equation of state. A sufficiently heavy pair may form a black hole promptly, leaving little time for a neutron star remnant. A lighter system may produce a hypermassive object that persists for milliseconds or longer. If the mass remains below the uniformly rotating limit, a supermassive remnant could survive much longer. The merger known as GW170817 brought these possibilities into observation. Two neutron stars in a galaxy about 130 million light-years away spiraled together and merged. Their combined gravitational mass before the collision was about 2.74 times the mass of the Sunday. During the inspiral, the stars raised tides on one another. The ease with which they deformed altered the phase of the gravitational wave signal. That tidal response depends strongly on radius and on the equation of state. A larger, less compact star deforms more readily. A smaller star resists through compactness. The measured waveform ruled out some of the stiffest models that predicted very large radii. The signal recorded by the detectors ended near the merger. The higher frequency waves from the remnant were too weak for the instruments to measure clearly. The immediate object left behind was therefore not seen directly in gravitational waves. Other messengers supplied clues. A short gamma-ray burst arrived roughly 2 seconds after the merger signal. Optical and infrared light followed from expanding radioactive debris. The event produced a kilonova, powered by the decay of newly formed heavy nuclei. Radio and X-ray emission later traced a narrow relativistic outflow interacting with surrounding material. Together, these signals suggest that the system did not collapse into a black hole before ejecting matter and launching its outflow. Many analyses favor a short-lived hypermassive neutron star, followed by collapse. Though the exact lifetime and sequence remain uncertain, the uncertainty is scientifically valuable. If the remnant avoided prompt collapse, despite its high total mass, the threshold for prompt black hole formation must have been higher than that total under the conditions of the merger. If it collapsed after losing differential rotation, the relation between that threshold and the TOV limit constrains the maximum mass of cold neutron stars. Such inferences depend on simulations. Researchers evolve the merger under general relativity, test many equations of state, and compare the resulting waves and ejecta with observation. The calculation must follow matter across a large change in density and temperature, while also tracking magnetic fields, neutrinos, and spacetime. The thresholds are not clean walls. Mass is lost in gravitational waves, neutrinos, and expelled matter. Some remains in a disk around the central object. The gravitational mass after merger is therefore lower than the simple sum measured before contact. Even so, the fate of the remnant carries information about the final stable mass. A promptly formed black hole would indicate that the combined core crossed the threshold almost at once. A delayed collapse allows a temporary neutron star phase. A long-lived remnant would require still greater support and would alter the energy deposited into the surrounding ejecta. Future events may reveal this sequence more directly. During the inspiral, gravitational waves rise in frequency as the orbit contracts. After contact, if a neutron star remnant survives, the signal changes. The merged object oscillates, deforms, and settles while continuing to radiate at frequencies of several thousand cycles per second. The earliest post-merger motion is complex. Several oscillation modes overlap. Spiral structures move through the remnant. The signal changes rapidly as angular momentum is redistributed. Later, simulations predict a quieter stage. The remnant can enter a long ring-down, radiating in a more regular tone after the most violent motion has faded. This is not the ring-down of a black hole. It comes from an extended object made of dense matter, still rotating and oscillating after the collision. Research published in 2025 identified a close relation between this late signal and the equation of state at the highest pressures reached in neutron star cores. In the simulations, the ratio between energy loss and angular momentum loss during the long ring-down tracked the behavior of matter at densities several times that of an atomic nucleus. The relation offers a different kind of measurement. Inspiral tides probe how the original stars deform before contact. X-ray pulse profiles probe the radii of isolated stars. The long ring-down would probe the compressed, heated remnant after two cores have become one. It reaches farther inward. No long ring-down signal from a binary neutron star merger has yet been measured with the precision needed for this test. Present detectors are least sensitive in the high-frequency range, where much of the post-merger radiation appears. The result is a prediction from general relativistic simulations and a guide for future observations, not a completed measurement. More sensitive instruments could change that. Third-generation gravitational wave observatories are designed to hear weaker and higher-frequency signals over greater distances. A nearby merger observed with sufficient clarity might reveal whether the remnant formed promptly, how long it survived, and how its late oscillations carried away energy. The last stable mass would then be approached from several directions at once. Heavy pulsars show that the limit must lie above them. Nicer radius measurements test how pressure grows with density. In-spiral waves measure tidal deformability. Post-merger waves could reveal the behavior of matter at still higher pressure. The fate of the remnant would connect those measurements to collapse itself. The TOV limit would remain an inferred boundary rather than a number written on any single star. Yet the allowed interval would narrow. At the boundary, there is no final material layer waiting to provide another ordinary form of support. Rotation can delay collapse. Heat can delay it. Differential motion can delay it. None changes the cold, non-rotating limit permanently. When those temporary supports fade, the star must settle below the limit or leave the family of neutron stars. The transition may be hidden behind an event horizon. To a distant observer, light from the surface becomes increasingly red and faint. The material continues inward, while signals from it take longer to escape. Once the horizon forms, no later message from the collapsing region can reach the outside universe. What lies beyond is described by a different object. Before that moment, the remnant may ring. Its frequency, fading pattern, and loss of angular momentum contain the final information that dense matter is able to send. The sound cannot travel through space as sound, but the changing geometry travels outward as gravitational waves. A boundary crossed in darkness leaves a pattern in space-time. A neutron star is born hot enough for matter to lose nearly every familiar form, but the heat does not remain. The object begins cooling almost at once. During its earliest moments, the interior is filled with trapped neutrinos, and those particles help carry pressure as the newborn remnant contracts. Within seconds, most of them escape. The star then enters a slower thermal life, one that can continue for millions of years. The first stage is governed mainly by neutrinos. Neutrinos interact so weakly that they can leave regions from which light cannot escape directly. Inside a young neutron star, they are produced in enormous numbers by reactions involving neutrons, protons, electrons, and other possible particles. Each neutrino carries only a small amount of energy, but the total flow cools the interior far more efficiently than radiation from the surface. The crust does not immediately share the same temperature as the core. Heat moves through it, while the core loses energy through neutrinos. After decades or centuries, the interior approaches a more uniform temperature, though magnetic fields still guide heat unevenly toward the surface. The surface tells only part of the story. A thin atmosphere changes the spectrum of the escaping X-rays. Hydrogen, carbon, and heavier elements each shape the radiation differently. The magnetic field can concentrate heat near the poles or insulate some regions, while allowing energy to flow more easily through others. A distant telescope therefore measures an apparent surface temperature, rather than placing a thermometer against the star. Age is uncertain as well. Some stars sit inside supernova remnants whose expansion gives an estimate. Others have an age inferred from rotation and spin-down, which can differ from the true time since birth. Distance and interstellar absorption add further uncertainty. Even with those difficulties, temperature remains a useful probe because different interiors lose energy at different rates. The slowest common neutrino process in ordinary nucleonic matter is known as modified URCA. In one version, a neutron changes into a proton while releasing an electron and an antineutrino, but another nearby nucleon must take part to conserve momentum. The extra participant makes the process less efficient. Direct URCA is faster, A neutron converts directly into a proton, an electron, and an antineutrino, while the reverse reaction produces a neutrino. No bystander is needed. The process can operate only when the proton fraction is high enough for the particle momenta to fit together. That threshold depends on the equation of state. In some models, direct URCA begins only in the cores of the most massive neutron stars. In others, it appears at lower mass. If it begins too easily, many young stars should cool below the observed temperatures. If it never begins, the coldest objects become difficult to explain. Hyperones or quark matter could open additional fast channels. Pairing among neutrons and protons can suppress some reactions, while creating another temporary source of neutrinos when pairs form and break. The thermal history is tied to the same microscopic interactions that determine pressure, radius, and maximum mass. Cooling is another view of the core. 3 isolated neutron stars brought that connection into sharper focus in 2024. Researchers reanalyzed observations from XMM Newton and Chandra and identified 3 objects that appear unusually cold for their young ages. Their surface temperatures are lower than expected under many standard cooling models. Their estimated ages place them in a period when thermal X-rays should still be comparatively strong. Yet they emit far less heat than many neutron stars of similar age. The discrepancy survives changes in assumed mass and magnetic field within the models tested by the research team. A minimal cooling framework, one that excludes the fastest neutrino channels associated with direct URCA or exotic matter, cannot reproduce the observations. Some efficient process must be available in at least part of the neutron star population. The study does not identify a single reaction. It requires viable equations of state to permit rapid cooling within some range of stellar masses. Applied to a broad model set, this condition rejects roughly 3/4 of the tested possibilities. A cold surface removes possibilities from deep inside. That result does not mean 3 stars have solved the composition of the core. Their ages, distances, atmospheres, and magnetic fields still carry uncertainty. The analysis compares families of thermal and structural models rather than observing one microscopic reaction directly. A fast channel is required, but several channels may produce similar cooling. The value lies in combination. A model that supports a 2 solar mass pulsar may still predict the wrong radius. One that matches nicer radii may cool young stars too slowly. Another may reproduce temperatures but make binary neutron stars too easy to deform during in-spiral. Each observation removes a different part of the allowed space. Radio timing begins with mass. In a binary system, the orbit can reveal how strongly the pulsar bends space-time around it. Delays in the arrival of radio pulses allow precise mass measurements. Those measurements establish that dense matter must support stars near or above twice the mass of the Sunday. X-ray pulse profiles add radius. Hot regions rotate across the surface, and gravity bends their light. The pulse shape reveals compactness. Several stars measured at different masses begin to trace how radius changes as more material is added. Thermal X-rays add cooling. The spectrum and luminosity reveal how much heat reaches the surface. With an age estimate, Langsley estimate, the observation constrains how rapidly the interior has lost energy. Gravitational waves add deformability. During a binary inspiral, each star raises a tide on the other. The distortion alters the waveform before contact. A larger radius generally allows greater deformation, while a more compact object changes shape less. After merger, a future detection of high-frequency waves could add the behavior of the remnant at still greater density and temperature. The signal may reveal whether the merged object survives briefly, rings for a time, or collapses quickly. The same star is rarely measured in all these ways at once. The population must be assembled like a scattered experiment. One object provides mass, another radius, 3 cold remnants constrain cooling, and a distant merger supplies tidal information. Together, they test the same relationship between pressure and density. This approach is called multi-messenger astronomy, when distinct carriers of information are combined. Light, radio waves, X-rays, gamma rays, neutrinos, and gravitational waves do not leave matter in the same way. Each passes through different regions and preserves a different part of the event. GW170817 provides a clear example. Gravitational waves trace the final orbits of two neutron stars. A gamma-ray burst follows. Optical and infrared light reveal radioactive ejecta. Later, radio and X-ray emission map the outflow as it moves through surrounding gas. Their timing and energy together constrain the merger, the viewing angle, the ejected matter, and the likely fate of the remnant. Isolated neutron stars require a quieter form of the same reasoning. Radio pulses measure rotation and mass. X-rays reveal temperature and surface geometry. Glitches expose internal exchange of angular momentum. The absence of continuous gravitational waves limits the size of permanent deformations. Silence becomes data as well. A detector that fails to find a predicted signal can rule out models that would have made it stronger. A warm surface can exclude a cooling channel that operates too efficiently. A heavy pulsar can eliminate a soft equation of state. A small tidal deformability can challenge a model that produces stars with large radii. The process works by shrinking the range of possible interiors. The cold stars from the 2024 study show how powerful a small, carefully chosen sample can become. Dozens of neutron stars have thermal measurements, but 3 unusual objects carry disproportionate weight because they occupy a region of age and temperature that many models cannot reach. Their faintness is the signal. A neutron star can also be reheated. Accretion deposits energy into the crust. Magnetic field decay can release heat in magnetars. Friction between internal components may slow cooling. Rotochemical heating can occur when spin-down changes the density and drives the material slightly away from chemical equilibrium, allowing reactions to restore balance and release energy. Old stars are therefore not always the coldest, and young stars are not always the hottest. Thermal evolution records both losses and hidden sources. This complexity prevents a simple ranking of temperature by age. A cooling crust after accretion measures thermal conductivity. A magnetar's decline probes magnetic energy and crustal transport. A millisecond pulsar may preserve heat through slow internal reactions. The equation of state governs structure, but thermal properties depend on more than pressure alone. Specific heat determines how much energy the material can store. Thermal conductivity controls how quickly that energy moves. Pairing gaps set when superfluidity and superconductivity appear. Neutrino emissivity determines how rapidly energy leaves the core. 2 models can produce similar masses and radii while cooling differently. This is why temperature adds information rather than repeating what geometry has shown. Mass and radius constrain the pressure supporting the star. Cooling constrains the particles and reactions carrying energy away. The same broad composition must satisfy both. The connection reaches back to the Sunday solar neutrinos reveal fusion in a core hidden from direct view. Neutron-star neutrinos are usually too faint and distant to detect individually, but their effect remains written into surface temperature. In both cases, weakly interacting particles carry information outward from a place light cannot describe directly. The scale has changed. The principle has not. A nearby supernova could one day provide a burst of neutrinos, gravitational waves from the collapse, and later thermal X-rays from the cooling surface. Such an event would connect the first seconds of the remnant to its early thermal life. For now, observations remain distributed across many objects and many decades. Each measurement is incomplete. The incomplete pieces overlap. The surviving equations of state must support heavy pulsars, fit measured radii, agree with tidal deformation, permit the observed cooling rates, and remain consistent with nuclear experiments. Some allow only nucleons. Some introduce new particles or phases at high density. None has yet been confirmed as the unique description of every neutron star. That uncertainty is the shape of the present boundary. A neutron star keeps most of its interior hidden behind a surface only a few tens of kilometers across. Its light is faint, its pulses are brief, its gravitational waves are smaller still. Yet those signals reach outward carrying traces of density, pressure, temperature, composition, and motion. The coldest young stars carry one of the quietest traces. They do not flare. They do not brighten the sky. They simply release less heat than expected. From that absence, entire models disappear. Far from the telescopes that record them, the three stars continue cooling. Neutrinos leave their cores without light. X-rays rise through thin atmospheres and cross the galaxy. The objects grow darker, while the information contained in that darkness becomes more precise. The descent into the neutron star ends without a direct view of the center. It ends with boundaries. Matter must be stiff enough to support great mass, compact enough to match the bending of light, deformable enough to shape a merger signal, and capable of cooling as quickly as the coldest young remnants demand. Inside those boundaries, several interiors remain possible. Outside them, the universe has already said no. The search for the interior of a neutron star does not end with a single measurement. It advances through overlap. A mass estimate reaches inward from one direction. A radius estimate reaches from another. Cooling adds a third boundary, while glitches, tidal deformation, and the fate of merger remnants press from the sides. Each signal is incomplete, but together they begin to describe a shape that no telescope can photograph. That shape is the equation of state. It is not a picture of particles in the ordinary sense. It is a relationship between pressure and density, written across conditions that range from the crust to the deepest central matter. Once that relationship is known, the size of a neutron star at a given mass can be calculated. Its maximum stable mass follows. So does the way it deforms in a binary system, and part of the way it cools. The difficulty is that many different interiors can imitate one another. A star made only of nucleons may produce nearly the same radius as a star with a small quark core. A model containing hyperons can be stiffened by stronger repulsive forces. A transition to a new phase can be hidden if it begins only in the most massive objects. Present observations often constrain families rather than selecting composition. This is why a single, well-measured star cannot finish the task. A lighter neutron star samples lower central density. A heavier star reaches further into matter that has been compressed for longer and under greater pressure. Two stars with the same mass but different temperatures may reveal different cooling channels. Two with similar temperatures but different ages may test the onset of superfluidity. A merger remnant reaches densities and temperatures not found in an isolated star. The population forms the experiment. The most useful observations are not always the brightest. A faint thermal spectrum can reject a cooling model. A small delay in radio pulses can refine a mass. A pulse profile gathered over years can shift a radius estimate by less than a kilometer. A gravitational wave signal too weak to show the remnant directly can still limit how easily the stars deformed before contact. The information arrives slowly because the effects are small. A neutron star does not reveal its central composition through one obvious feature. There is no spectral line labeled quark matter. There is no pulse that announces the arrival of hyperons. Instead, the presence of new particles changes pressure, heat capacity, neutrino emission, and the speed at which the star responds to disturbance. The evidence is distributed across several kinds of behavior. This makes uncertainty part of the measurement rather than a weakness to be removed from the story. A mass may be known precisely, while the radius remains broad. A temperature may depend on an uncertain atmosphere. A cooling age may rely on a supernova remnant whose own history is not fully known. Gravitational wave measurements can depend on detector sensitivity and the way the waveform is modeled. Every result carries a range. Those ranges overlap. Where they fail to overlap, a model disappears. The process is quiet, but it is severe. An equation of state may reproduce one pulsar and fail to support another. It may produce acceptable radii, yet cool young stars too slowly. It may fit isolated objects and predict tidal deformation that is too large during a merger. Dense matter theories survive only by passing all of these tests at once. The equation of state is assembled across the population, much as the structure of ordinary stars was assembled from many spectra, pulsations, and evolutionary stages. The work proceeds by connecting signals that at first appear unrelated. A pulse arriving early and a surface cooling too quickly may both depend on neutron pairing. A large mass and a modest radius may both limit how soft the central matter can become. A weak tidal deformation and a short-lived merger remnant may point toward the same region of pressure and density. The connections are indirect, yet they are physical. As measurements improve, some uncertainties will shrink, while others become more visible. Better radius estimates may expose disagreement between atmosphere models. More precise masses may reveal that the heaviest known pulsars cluster below a real upper boundary. A nearby merger may provide a post-merger signal and show whether the remnant survives for milliseconds, seconds, or much longer. The result may not be one simple answer. Dense matter could change phase more than once. Neutrons and protons may dominate the outer core, hyperones may appear deeper down, and quarks may become relevant only in the most massive stars. Pairing patterns may vary with density. The interior could contain several transitions rather than one central substance. A neutron star may be less like a uniform ball and more like a sequence of physical regimes, each stable only within a narrow range of pressure. Even if the composition is eventually identified, another question remains. How accurately do the known laws describe gravity under these conditions? General relativity has passed every neutron star test available so far. Binary timing, pulse delays, gravitational waves, and the motion of compact systems continue to agree with it. Yet agreement does not prove that no deeper theory exists. Neutron stars combine strong gravity with quantum matter. Their structure depends on both, but current calculations usually treat gravity through general relativity and matter through quantum many-body physics without a complete quantum theory of spacetime. The approach works, though the two frameworks are not fully united. The core may never reach the conditions needed to expose that mismatch directly. It may simply provide stricter limits on where deviations could hide. That is still useful. A theory that changes gravity must reproduce measured masses, radii, orbits, and merger waveforms. Most possible changes are eliminated long before they become visible as dramatic effects. The universe permits little freedom once enough measurements are combined. This is one reason neutron stars remain valuable even when the central composition is uncertain. Their uncertainty is structured. It is bounded by observed mass, by the bending of light, by cooling, by timing, and by waves in spacetime. The unknown region is not empty. It has edges. The first models treated neutron stars as simple collections of ideal particles. Later work added nuclear forces, superfluidity, superconductivity, magnetic fields, relativistic rotation, and new particle species. Each addition made the interior less simple, but also more connected to observation. The modern picture is not finished. It is closer to the star itself, layered, compressed, and held between competing tendencies. Gravity gathers matter inward. Quantum rules resist crowding. Nuclear forces attract and repel across tiny distances. Rotation provides temporary support. Magnetic fields move energy and stress through the crust. Neutrinos remove heat from places light cannot reach. Every part changes the others. The neutron star remains stable only while these processes find a shared arrangement. That stability can last for longer than recorded human history. A pulsar can continue turning, cooling, and slowing while civilizations appear and disappear beneath its distant light. Its internal components adjust by amounts too small to see, except when a pulse shifts or a surface temperature falls outside expectation. The star does not need to cross a final threshold to teach anything. Its continued existence is already a measurement. A neutron star with twice the mass of the Sun proves that dense matter can produce enough pressure to avoid collapse. A radius near the size of a city shows how tightly that mass can be confined. A cold surface proves that energy can leave through channels hidden beneath the crust. A glitch proves that part of the interior can preserve motion apart from the observable shell. Each fact describes a limit. Placed together, the limits form a narrow path through possible physics. The correct description of dense matter must fit along that path without stepping outside it. There may still be room for unexpected phases. There may be particles not yet placed confidently in the core. There may be transitions that appear only in the heaviest stars. The evidence does not close every possibility. It changes the scale of the unknown. The center is no longer simply a blank region beneath an unreachable surface. It is a constrained environment with a measured pressure range, a limited set of viable cooling behaviors, and a maximum mass that cannot be chosen freely. Every new observation removes another way for matter to behave. The search continues through patience. More pulses are counted. More thermal photons are collected. More binary orbits are timed. Detectors remain quiet until another merger crosses their range. The work is cumulative, and the answer, if it comes, will likely emerge from agreement among many small signals rather than from one decisive moment. The star keeps turning while the measurements gather. Deep below its surface, the matter does not know that it is being studied. Neutrons pair, vortices move, heat travels outward, pressure rises toward the center, the structure holds. For now, that is enough. The neutron star continues to turn in the dark, carrying its hidden layers without effort and without explanation. The measurements can rest now. Mass, radius, pressure, and temperature can drift away from attention, leaving only the slow image of a small star suspended in a wide and quiet sky. Nothing more needs to be followed. The distant pulses continue whether anyone is listening or not. They cross the space between stars, pass through cold clouds of gas, and move onward into regions where no telescope is waiting. The star keeps its rhythm. The darkness keeps its distance. The room can become part of that quiet. Breathing may slow. The weight of the body can settle more fully into the surface beneath it. The last thoughts of equations and hidden matter can loosen and fade, no longer needing to be held in place. Far away, the neutron star cools by degrees too small to notice. Its surface turns beneath faint light. Deep below, the unseen structure remains compressed, stable, and still. There is no need to imagine the center any longer. The universe can keep what remains unknown. Beyond the walls, beyond the atmosphere, beyond the familiar stars, space opens without sound. The long path inward is complete. The pressure, the motion, and the faint signals have all receded into darkness. Only the turning remains. One rotation follows another, steady and distant. The star grows no closer. The night asks nothing more. The darkness can hold the unanswered questions. The body can release them, and the journey can end here, in the calm between one pulse and the next. Is greater than, is greater than, is greater than. End of script. Sleep well.